So, welcome to today class of nonlinear vibration. Today class will discuss about the nonlinear force vibration of single and multi degree of freedom systems. Already we are discussing the single degree of freedom systems. So, here we have seen how one can apply a weak forcing or strong forcing in the system, and we have studied up to the superharmonic resonance condition in case of hard excitation. So, today class will make a revision of this single degree of freedom system, and also briefly we will introduce about this multi degree of freedom system, and next class will study in detail about the multi degree of freedom system force vibration. So, as we know that, so in this class we will see how the governing equation motion of single and multi degree of freedom system considering weak and hard forcing term has been derived. Then solution methods, determination of steady state response, comparison of linear and nonlinear system response. So, we know that let us start from a multi degree of freedom system, and we will see how our the single degree of freedom system analysis can be reduced to that of a or how the knowledge of the single degree of freedom systems can be extended to that of a multi degree of freedom system. So, for example, let us take this 2 spring mass system. So, this is a mass and this is the second mass, and we have springs and dampers attached to the systems. So, or in okay. So, let us put a system like this, simple system. So, in this case this is K1, this is M1, this is K2, M2 and K3. So, if we make this spring K1 or this first spring nonlinear and the third spring nonlinear, so we can write the equation motion. So, the equation motion for this case can be written in this form, that is a mass matrix. So, if we are writing this is x1 and this is x2, then for this spring it will be the spring force will be, we can write this spring force equal to K1 into, let me put in this way. So, K1 into or K1x, K1 spring force F1 equal to K1x plus, as it is we are assuming to be nonlinear, then I can put this is equal to epsilon K1, let it is cubic nonlinear. So, it will be epsilon K1 x cube. Similarly, this for the third spring we can write the spring force equal to K3 x2 plus, so this is K1 x1 and this is x1, because this spring first spring will be extended by an amount x1. So, K3 x2 plus, let me put it epsilon K2 x2 cube. So, this way we can introduce the nonlinearity in the system. So, this fast mass, or if you write the free body diagram of the fast mass, that is M1. So, this case can be written in this form. So, this is subjected to a displacement x1 towards right. So, it will be subjected to a inertia force of M1 x1 double dot towards left. Similarly, the spring force F1 already we have spring force F1 which is nonlinear, and this damping force also. So, damping force which will be, so if this is C1, so this will be equal to C1 x1 dot. And so, as the spring K2, so let us assume a linear spring. So, assuming a linear spring, so this will have a relative motion of x1 minus x2. So, this x1 minus x2 force will be equal to in this direction x1 minus x2. Similarly, we can write the equation motion of the second mass. So, this is mass M2. So, due to this inertia force, so as it is moving towards right, the inertia force will act towards left, that is M2 x2 double dot, and then the other forces will be equal to. So, this is F3, that is the nonlinear spring force, and we can have this. So, let me write this is C3, then it will be C3 x2 double dot. Similarly, this force will be equal to, so this force I can write, so this will be equal to K2 into x2 minus x1. So, K2 into x1 minus x2 force will act towards right, and we can write this force towards left like this. So, m K2 into x2 minus x1. So, combining these, so we can write, or we can write this equation motion in this form, that means m1 x1 double dot m1 x1 double dot plus f1. So, for f1 I can write this equation in this form, that is k1 x1 plus epsilon k1 x1 cube. So, this is f1, then plus c1 x1 dot c1 x1 dot. So, if I am applying a force, let me apply a force capital F1 F1 sin omega t. So, that force, so this will be equal to F1 sin omega 1 t. So, I can write this equation equal to F1 sin omega 1 t. So, this way one can write the first equation, and the second equation can be written from this. So, which is m2 x2 double dot plus k2 x2. So, one can write this force. Okay. So, in the first equation I have to add this force k2 into x1 minus x2. So, it is not been added. So, plus k2 into x1 minus x2. So, this will be equal to f1 sin omega t. Similarly, for the second equation m2 x2 double dot plus k2 x2 minus x1 plus f3 is k3 x2 plus k3 x2. So, plus k3 x2 plus epsilon k2 plus epsilon k2 x2 square x2 cube. Let us see. So, what are the other forces acting? So, damping force plus C3. So, damping force is x2 dot, not x2 double dot, C3 x2 dot. So, plus C3 x2 dot. So, this will be equal to 0. So, let us see what we have written. So, m2 x2 double dot. So, this is the force acting this way, plus k2 into x2 minus x1, k2 into minus k2 x1 is there. So, minus k2 x1, k2 into x2 minus x1. So, minus k2 minus x1. So, this way we have written. So, this is the equation motion. So, this equation motion can be written in matrix form also. So, in matrix form this will be equal to m1 0 0 m2. So, this becomes x1 double dot x2 double dot plus, let us write the linear part in this way. So, this will be k1 x1. So, this is plus k2. So, k1 plus k2 x1 minus k2 minus k1, okay, minus k2 into x2. So, minus k2. So, then okay. So, this is the only linear term, that is x1 x2, and for the second equation it can be written minus k2, and this becomes k2 x2 plus, let us see, k3 x2. So, this will be equal to k2 plus k3. So, plus the damping term also can be written. So, damping term, this is C1 0 0 C2. So, this is x1 dot x2 dot. So, plus then the nonlinear terms let us write. So, the nonlinear terms in the first equation becomes epsilon k1 x1 cube, and in the second equation, so in the second equation this is equal to epsilon k2 x2 cube. So, this will be equal to f1 sin omega 1 t and 0. So, this is the equation motion of a nonlinear 2 degree of freedom system, and this equation, and in this equation the analysis can be made similar to that of the single degree of freedom system also. So, in case of single degree of freedom system, so we have studied about the weak forcing and also about the strong forcing. So, if now we can see that this equation is a coupled equation here, though the mass matrix is uncoupled, the stiffness matrix is coupled. So, here the stiffness matrix is coupled because in the first equation itself we have the term with x 2. The first equation we have the term with x 2. So, that is why we have coupled stiffness matrix, and though the coupling is not in mass matrix. So, we have coupling in the stiffness matrix. So, we can write this equation in a uncoupled form, or the linear part can be written, at least the linear part can be written in an uncoupled form by using this modal analysis method. That means, we can find the dynamic matrix. So, A, let us find dynamic matrix A equal to M inverse K. So, if you write A equal to M inverse K and find the eigenvalue of this. So, if we find the eigenvalue of this and eigenvector of this, then we can write the modal matrix. So, we can write the modal matrix. So, in this case corresponding to these two. So, this is a 2 degree of freedom system. So, we will have 2 eigenvalues, and corresponding to these 2 eigenvalue we will have 2 eigenvectors. So, using these 2 eigenvectors, so we can uncouple this equation by writing. So, by using this thing P transpose M P. So, by taking, let us take this x equal to P y. So, if you take x equal to P y, then we can have this P transpose M P y double dot plus P transpose K P y. So, here y equal to y 1 and y 2, like x equal to x 1 and x 2. So, y equal to, so this x equal to x 1 and x 2, similarly y equal to y 1 and y 2. So, then plus we can have this P transpose C. So, P transpose C P y plus P transpose. So, we can write this nonlinear part also by substituting this thing. So, now by substituting this, so we can write this nonlinear part epsilon k 1 x 1 cube and epsilon k 2 x 2 cube. So, we can write the nonlinear part also by multiplying this P transpose into P 1. So, that is equal to epsilon k 1 So, we can substitute that thing. So, by substituting we can write, or we have to substitute this part epsilon k 1 x 1 cube and epsilon k 2 x 2 cube. So, x 2 cube. So, we have to substitute the corresponding value of x 1 and x 2 here. Similarly, we can have to write this P 1 transpose. So, you have to multiply this P transpose here. So, P 1 transpose. So, this is the forcing function. So, this way we can uncouple the mass matrix and stiffness matrix, and we can have a equation, uncoupled equation at least in mass and stiffness, and this equation can be written in this form, that is y 1 double dot plus omega 1 square y 1 plus 2 zeta omega 1 y 1 plus. So, we will have a forcing term. So, this forcing term may contain this x 1 x 2 and derivative of that. So, this will be equal to a forcing term f 1. Similarly, we will have second equation y 2 double dot plus omega 2 square y 2 plus 2 zeta 1 zeta 2 omega 2 y 2 plus this is f 1, this is f 2. So, this is a function of x 1 x 2. So, these are the nonlinear terms in the system, and this will be equal to f 2. So, we will have a set of 2 equations now, where these first 2 terms, that is the coefficient of the coefficient of y double dot and coefficient of y 1 are uncoupled. So, here we can use the method what we have studied for the single degree of freedom system, and we can solve these two nonlinear equations. So, we can solve these two nonlinear equations simultaneously by applying the different methods what we have studied. So, tomorrow class will apply the method of harmonic balance to the system, and today class will just now revise how we have used this method of multiple scale to a single degree of freedom system and found the response of the system. So, up to superharmonic resonance conditions we have studied last class, and today we will revise about or we will study how we can apply the subharmonic resonance also in case of combination, or if we have more than one forcing or multi frequency excitation terms will be there, then how we have to find the response by using method of multiple scale. So, here, so now these equations are reduced to that of a single degree of freedom system, and now we can apply the method of multiple scale to study this thing. So, in our previous class we have taken, so if the system is of weak nonlinearity, so taking only a cubic nonlinear term, so we can have this primary resonance. Primary resonance means this omega external forcing when it is equal to near the natural frequency of the system, then we can add a detuning parameter to the system, and by substituting. So, if our equation is reduced to this form, then we can substituting this u equal to u 0 plus epsilon u 1. So, we will get this forcing term. So, this forcing term by using the detuning parameter we can write in this way, and then by using method of multiple scale and separating the order of epsilon terms. So, we can have this d 0 square u 0 plus omega 0 square u 0 equal to 0. Then the solution of this term equal is this. So, where we can write u 0 equal to a t 1 e to the power I omega 0 t 1 t 0 plus a bar t 1 e to the power minus I omega 0 t 0. So, here, so a bar is the complex conjugate of a. So, by substituting this equation in the second equation, where we have this term with u 1, that means we have written this u, that is the displacement of the system in by using two terms, one is u 0 and another one is epsilon u 1. So, this is similar to, let us take a number 10.23. So, here, so we can write this number in this form, that is the solution can be of 10 plus epsilon into 2 plus epsilon square into 3. So, if you are taking this epsilon equal to 0.1, so then this becomes 10.2, the solution will be 10.2, and if you are taking, okay, so we are as we are taking epsilon equal to 0.1, so epsilon square equal to 0.01 and multiplying this thing, this becomes 0.03. So, the solution will becomes 10.2 plus 0.03, so 10.23. So, if we are not taking this epsilon term, this that means epsilon u 1 plus epsilon square u 2, then we may get a solution equal to 10, but if we want to get the precise solution, then we have to take the higher order terms. So, when we will take the higher order terms, we get this additional term, that is epsilon, that is 0.2, 0.2 will correspond to u 1, similarly 0.3 will correspond to u 2. So, this way we can take different additional term in u to get the precise solution of the system. So, we can write in here we have written this u equal to u 0 plus epsilon u 1, and here we have assumed this u is a function of t 0 and t 1, where t 0 equal to the time t and t 1 is equal to epsilon t 0 or epsilon t, as t 0 equal to t 1. So, t 1 as t 0 equal to the time. So, t 1 becomes epsilon t. So, now substituting the second equation, this equation in this equation, so which is written in terms of u 1. So, we can have some terms which leads to infinite resonance condition or infinite response of the system or unbounded response of the system. So, this thing happen if a term. So, from the left side we can see that it contains d 0 square u 1 plus omega 0 square u 1. So, any term or any term in the right hand side containing e to the power I omega 0 t 0. So, will be a secular term or will lead to infinite resonance or infinite response, but in actual case the system is bounded. So, we have to eliminate these terms which are known as the secular term. So, here one can see that this is a secular term. So, we can write this equation using this complex conjugate also. So, writing this equation in terms of its complex conjugate. So, one can write in this way. So, one can see that the terms this has to be eliminated as this is coefficient of e to the power I omega 0 t 0, which will lead to unbounded solution. Similarly, this term, so for small value of sigma, so this term is also a secular term or this term will be unbounded. So, one can take this term and this term. So, to get the total secular and mixed secular term and eliminate these secular and mixed or sometimes it can be told near secular. So, one can eliminate the secular or mixed secular term to get the response of the system. So, now eliminating this one can obtain. So, one can have two things, one can get the resonant condition or one can study the non-resonant condition. So, in case of non-resonant condition, as already we have discussed, due to the presence of damping, so it will lead to it will decay and one can get the steady state solution in this form. So, it will decay. So, A 2 equal to A 2 e to the power minus mu 2 T 1. So, it will exponentially decay to the steady state solution or trivial response. And in case of non-resonant condition, so we can take. So, if you are considering this internal resonance type, we can take omega 2 equal to 2 omega 1. So, depending on the resonance condition, internal resonance condition, if someone take, then he has to take in this form, and already we have discussed this thing, and it will reduce to a set of reduced equation from which we can get. So, these are the reduced equation, and to write in autonomous form. So, we can use this gamma. So, it will reduce to a set of equation. So, for steady state it reduced to this equation. So, one can get a closed form solution this. So, for the non-resonant condition, so one will get a steady state solution. So, this equation one can see this is 6th order in A or quadratic in sigma. Sigma is the detuning parameter, A is the response of the system. So, as it is quadratic in terms of sigma, so one can find the response of the system by using the quadratic equation, and the solution of the overall solution of the system can be written in this form. So, u equal to A cos omega t minus gamma, that means the system will oscillate with a frequency of external excitation in case of the non-resonant condition or. So, this is the thing what we have discussed for a system if it is weakly nonlinear, and this is the relation between the detuning parameter and response amplitude. So, by plotting the response amplitude versus detuning parameter sigma, so one can get the response like this. So, where one can observe the jump up or jump down phenomena, and also one can study the stability of the system by finding the eigenvalue of the equations, these two reduced equation. So, by finding the eigenvalue of these two reduced equation, so by finding the Jacobian matrix and finding the eigenvalue of the Jacobian matrix. So, one can find or one can study the stability of the system. The response, steady state response will be stable if the real part of the eigenvalue becomes negative, and it is unstable if the real part of the eigenvalue is positive. So, one can plot. So, one can study the effect of nonlinearity. So, here by sweeping off, so one can, so if it is supercritical, so one can follow this curve. So, it will go up, but while sweeping down the frequency. So, this is A versus sigma. So, by sweeping down the frequency, one can observe. So, as here this branch is unstable. So, by sweeping down, so one has a jump up phenomena here. So, it will, the response will jump up and it will follow this curve again. So, one can have this jump up and jump down phenomena. Already we have discussed about the stability of the system. So, in this way, in case of weak nonlinear system, one can study the system. So, when the equation is hard excitation, that means when we cannot write the forcing term as epsilon f cos omega t in the equation motion. So, here we are not using this epsilon. So, previous case we have written it is equal to epsilon f cos omega t, but in this case as this term is no longer small. So, we cannot use this word epsilon, and so this equation can be written as f cos omega t 0. So, by proceeding in the similar way, so using method of multiple scale, so we can see that the solution of this equation will contain two parts. Previously, as this right hand side was 0, so we have only the complementary part, but now in addition to this complementary part, we have to add the particular integral to the system, particular integral of the system. So, the complementary part becomes a t 1 e to the power I omega t 0 plus its complex conjugate, that is a bar e to the power minus I omega 0 t 0, and plus the particular integral part of this will be equal to half f by omega 0 square minus omega square into e to the power I omega t 0 plus its complex conjugate. So, this way one can write. So, this is the additional term in equation u 0 when we are considering the excitation to be hard. So, in case of hard excitation, we have seen the response u 0 can be written in this form. Now, by writing this equation in this form and substituting this in the second equation, and we can see there are several resonance conditions available in the system, or several terms will lead to unbounded solution. So, one has to study. So, what are the conditions for which the system response becomes unbounded. So, here what we have seen. So, this is one term. The first term is the secular term because it is coefficient of e to the power I omega 0 t 0, and the second term, in the second term we have the condition, that means when this capital omega. So, this is equal to, or this 3 omega nearly equal to omega 0. So, we will have resonance condition. So, we have seen the different type of resonance condition. So, first one can study the non-resonant case. In non-resonant case, similar to previous, so it will decay. So, we have the superharmonic resonance condition. So, we have seen the case 3 omega equal to omega 0. So, that is known as superharmonic resonance condition, because in this case the system will oscillate at a frequency equal to omega, which is equal to 1/3 omega 0. So, this is superharmonic resonance condition. So, proceeding in the previous way. So, we can write this 3 omega equal to omega 0 plus epsilon sigma. So, sigma is the detuning parameter. Now, so eliminating the secular term for this resonance condition. So, we can have a set of reduced equation. So, these are the set of reduced equation. So, and by solving, so for steady state solution as the steady state is not a function of time. So, this time derivative terms would not be present in the system. So, by putting this A dash equal to 0 and beta dash equal to 0, so we can have a set of equation. So, we will have a set of equation. So, these are the equation. So, here to make the system autonomous, so we have substituted this gamma equal to, so gamma equal to sigma T 1 minus beta. By substituting gamma equal to sigma T 1 minus beta, so we have written this equation. So, this is the first order solution of the system. So, u equal to A cos 3 omega. So, this is A cos 3 omega t minus gamma plus f by omega 0 square minus omega square cos omega t plus order of epsilon. So, for steady state already we have seen, so it will reduce to that of a closed form solution. So, this is the closed form solution written in terms of sigma and A. Sigma is the detuning parameter of the system and A is the amplitude, here mu is the damping parameter of the system, and this term represent the forcing parameter of the system. So, one can plot this equation for different amplitude of forcing, different amplitude of mu, that is damping, and plot the frequency response of the system. So, here sigma, so this is the closed form solution of sigma, because in this equation we have written sigma as sigma is a quadratic. In this equation it appears as a quadratic form of sigma or sixth order form of A. So, one can either numerically solve this equation for A or write or solve this quadratic equation and solve to write the sigma equal to this. By getting sigma in this form, so one can find the response of the system, and last class we have seen the response of the system. So, here one can see or observe from this equation the free vibration term of the system and the force vibration term of the system, and one can observe that the free vibration amplitude of the system equal to alpha lambda mu q by omega mu omega 0, and the corresponding detuning parameter is this. So, this is the super harmonic resonance condition, and one can also study the subharmonic resonance condition in. So, from this equation already we have seen the condition 3 omega equal to. So, 3 omega equal to, by substituting 3 omega equal to omega 0. So, we have seen one resonance condition, and the next resonance condition one can observe. So, when omega minus 2 omega 0 equal to omega 0, omega minus 2 omega 0 equal to omega 0 or omega equal to 3 omega 0. So, this also leads to a resonance condition. So, in this case, so another condition is omega minus 2 omega equal to omega 0 or this omega equal to 0. So, omega is 0, omega equal to 0 means we have a fixed amplitude. So, our forcing function, as our forcing function is omega cos omega t, putting this omega equal to 0. So, we will have a fixed amplitude forcing. So, we are not considering that term. So, now let us see this case when this external excitation frequency omega is near to 3 times omega 0 of the system. So, if it is 3 times, then it is known as subharmonic resonance condition. So, in case of subharmonic resonance condition, so we have taken omega nearly equal to 3 times omega 0 or this external frequency omega equal to 3 omega 0 plus epsilon sigma. So, here this forcing term. So, in the forcing term we have this omega minus 2 omega 0 t 0. So, that thing can be written as, so 3 omega 0 into t 0 minus 2 omega 0 t 0. So, this becomes omega 0 t 0 plus epsilon sigma t 0. So, as epsilon t 0 equal to sigma epsilon T0 equal to T1. So, we can write this equal to omega 0 T0 plus, so we can write this equal to omega 0 T0 plus sigma T1. So, this term can be written in this way, omega 0 T0 plus sigma T1, and substituting that equation. So, this leads to the secular term. So, this term has to be eliminated from that equation. So, now proceeding in the similar way by substituting A equal to half e to the power I beta, half e to the power I beta, and separating the real and imaginary part. So, we obtain these two equations, that is A dash equal to minus mu a minus 3 alpha lambda by 4 omega 0 a square sin sigma T1 minus 3 beta, and A b dash equal to 3 alpha by omega 0 into lambda square plus 1 by 8 a square into a plus 3 alpha lambda a square by 4 omega 0 cos sigma T1 minus 3 beta. So, to make it non-autonomous, so in this equation this time appear explicitly in this equation. So, to make the system non-autonomous, we can substitute the sigma T1 minus 3 beta equal to gamma and write this equation in this form. So, that is A dash, where A dash is differentiation of A with respect to T1. So, this writing this A dash and gamma dash equation we can write. So, now we can write the solution of the system in this form. So, solution of the system u equal to A cos 1/3 omega t minus gamma plus, so plus we have this forcing term f omega 0 square minus omega square to the power minus 1 cos omega t plus this. So, this way we can write the solution of the system, where for steady state eliminating this A dash and gamma dash or substituting A dash and gamma dash equal to 0. So, we have these two equation. So, in these equation eliminating this cos gamma and sin gamma. So, we can have this closed form solution. So, in this closed form solution one can see, so this is a square and this right side it is a fourth. So, one can take this a square term common. So, that means some term into a square equal to 0. So, either a square equal to 0 or this term equal to 0. So, for steady state eliminating this gamma, either we can see this a square equal to 0 or this equal to 0. So, a square equal to 0 correspond to the trivial state of the system. So, either, so in this case that means a trivial state exists in the system. So, either the trivial state will be stable or unstable. So, one can study by perturbing this reduced equation and studying the Jacobian matrix, eigenvalue of the Jacobian matrix. And for the case of non-trivial solution, so in this case one can find this a square equal to, so from this as it is in quadratic form, so one can write this a square equal to p plus minus root over p square minus q, and where p equal to 8 omega 0 sigma by 9 alpha minus 6 lambda square, and q equal to 64 omega 0 square by 81 alpha square into 9 mu square plus sigma minus 9 alpha lambda square by omega 0 square. So, it can be noted that, so from this equation the solution will exist. The solution will exist if this part is, or will have a real solution if this part is positive. So, the solution will exist if this p square greater than q, or if p square is not greater than q, then we cannot have a real solution. So, to have a real solution, so p square should be greater than q. So, in this condition, so one can obtain a condition from this, so which will lead or which will give rise to the non-trivial state of the system. So, one can find the trivial state. So, in this case both trivial and non-trivial state of the system exists. So, one can plot the response of the system from this using this detuning parameter, and one can study the stability of the system also. So, in this way, so we can have the subharmonic or superharmonic resonance condition along with the primary resonance condition when we have either a So, when we have soft excitation or hard excitation of a single degree of freedom system, and already we have seen, so we can reduce a multi degree of freedom system to that of a single degree of freedom system, and we can make similar analysis to obtain the response of the system. Also, a continuous system can be reduced to that of a single degree of freedom system by using the generalized Galerkin method, where we can take a single mode approximation. So, by taking a single mode approximation, so we can reduce the continuous system to that of a single degree of freedom system, or by taking multi-mode approximation. So, taking a multi-mode approximation, we can reduce the equation to that of a multi degree of freedom system. So, the single degree of freedom system analysis is very much important before studying the multi degree and continuous system, as one can use this single degree of freedom system analysis for finding the response of a system with multi degree of freedom. So, let us see. So, if a multi frequency excitation acts on the system, what will happen to the system? So, previously we have taken only a single term, single forcing term. So, we can take, instead of taking a single forcing term, we can take multiple forcing term. So, let us take the case when this forcing term equal to k 1 cos omega 1 t plus theta 1 plus k 2 cos omega 2 t plus theta 2. So, one can reduce these two forcing term to a single forcing term. Either one can reduce these two to a single forcing term, or one can use these two terms and solve the response of the system to find solve the equation of the system to find the response of the system. So, like previous case, here also we can take u equal to u 0 plus epsilon u 1. Then our equation, that is the equation what you have used before, that is u double dot plus omega 0 square u plus epsilon mu 2 epsilon mu u dot plus alpha epsilon alpha u cube equal to. So, here we are taking this equal to f 1 f t. So, where f t equal to combination of two harmonics or combination of two frequency. So, this is two frequency excitation. Similarly, one can take the system with multi frequency excitation. So, in this case, either one can study the system by taking this forcing as weak forcing, or one can study the system by taking this as hard excitation. So, in case of weak excitation, or in case of hard excitation, one can write the system equation in this form, that is d 0 square u 0 plus omega 0 square u 0 will be equal to k 1 cos omega 1 t 0 plus theta 1 plus k 2 cos omega 2 t 0 plus theta 2. So, in this case, in contrast to the single degree of freedom system, one can observe that one can get a number of resonance conditions. So, here by taking this u 0 equal to, so similar to the previous case. So, here the u 0 will contain a complementary part and the particular solution due to this one and plus due to this term. So, one can write the particular solution with omega 1 this, and for this is for forcing k 1 and this is for forcing k 2 in addition to the complementary part solution, that is a t 1 e to the power I omega 0 t 0. So, by writing this u 0 or substituting this u 0 in this equation of u 1 and eliminating the secular terms, one can get different resonance conditions. So, while eliminating the secular condition, one should pay attention to the terms which lead to the secular term or mixed secular term or near secular term. For example, we have studied this is the superharmonic resonance, that means when this 3 omega 1 nearly equal to omega 1. Similarly, we can have the terms. So, we can have, one can see that we can have a number of resonance condition. So, these are the number of resonance condition one can obtain. So, these are super harmonic or subharmonic, and in addition to that one can have the secondary primary resonance condition, secondary resonance conditions. So, in case of primary resonance condition, so the resonance will be near to the natural frequency of the system. When it is not near to the natural frequency of the system, so we can get this secondary resonance condition. So, from the previous equation one can see the resonance will happen. So, when this omega 0 nearly equal to 3 omega n, similarly this omega 0 equal to 1/3 omega n. Similarly, one can see this condition, that is omega 0 equal to 1 plus minus 2 omega m plus minus omega n, and omega 0 nearly equal to half omega m plus minus omega n. So, in this case, so this is known as, so these are primary resonance and these are combination resonance. So, as we are taking combination of two frequency here, so this is combination resonance. So, combination resonance condition. So, one can have primary resonance and combination resonance in this case. So, taking these resonance condition or taking these two conditions, so one can see in these two frequency excitation one can have these different types of resonance condition. That means, omega 0 nearly equal to 3 omega 1 or 3 omega 2, we can get this response. Similarly, omega 0 equal to 1/3 omega 1. So, one case is the super harmonic resonance, other case is the subharmonic resonance condition, and these leads to the combination resonance of the system. So, we can have this primary resonance or combination resonance of the system. So, in this way, so for each resonance condition, as we have studied in the last, or we have discussed in the last section. So, here also for each resonance condition, so we have to study the system separately and we have to find the response of the system. So, by taking different resonance condition, first we have to write the reduced equation, then in this reduced equation we have to substitute the time varying term equal to 0 to get the steady state solution, and from the steady state solution we have to find the, so we have to find the equation, or we have to find the frequency amplitude relation equation, and from that we can obtain either a closed form solution, or in case of multi degree of freedom system we can get a set of equations. For example, in case of 2 degree of freedom system, as we have 2 equation, so we can expand this u1 and or x1 and x2 in terms of. So, in our case, the example what we have taken in this case, that means we have x1. So, this x1 we can expand it in this form, x1 can be written this x10 plus epsilon x11 plus epsilon square x12 plus higher order terms. Similarly, one can write this x2 equal to x20 plus epsilon x21 plus epsilon square x22 and higher order terms. So, now substituting this equation in the original equation and separating the terms of the order of epsilon and epsilon to the power 0, epsilon to the power 1 and 2. So, we can get a set of equations. So, from these equations we can get, so we can get the reduced equation. So, in this case we will have 4 reduced equation. So, one will be in terms of A1, other will be in terms of gamma 1, second one will be A2 and gamma 2. So, we will have a equation A1 dash, gamma 1 dash, A2 dash and gamma 2 dash. So, we will have 4 equation, unlike in case of single degree of freedom system where we have 2 equations. In this case we will have 4 equations. So, getting a closed form solution in this case will be difficult. So, in this case one has to solve this equation, or by substituting this A1 dash, gamma 1 dash, A2 dash, gamma 2 dash equal to 0. So, one can get the equation for the steady state, but these 4 equation, these 4 nonlinear algebraic and transcendental equations can be solved numerically. So, one has to solve numerically these equations. So, one has to solve numerically these equations to obtain the response of the system. So, to solve these equation numerically, one may use the Newton's method. So, one may use the Newton's method to find the solution of the system. So, unlike in case of single degree of freedom system where we are getting a maximum of 3 branches. So, in this case we may get multiple solutions or multiple branch solutions. So, one has to apply this Newton's method properly to find this solution of the system. Also, one may note that in this Newton method, so it depends on the initial condition. So, for different initial condition, as different initial condition will leads to different equilibrium position. So, one should be very careful in applying this Newton's method to obtain this multi-branch solution of the system. So, next class we will see some examples and also how to use this harmonic balance method for finding the solution of a multi degree of freedom forced response of a system. Thank you.